we have here a compilation of what we did last time. And so what was the idea last time? So we're introducing this notion called the Laplace transform. And what we do is we take a function, f of t, and we do something to it. And at the end, we produce a new function, f of s. And what we do to this to make the function, there's a rule, is for any value of s, we carry out the integral. 0 to infinity, e to the minus st f of t dt. Now you'll notice because we're integrating with respect to t, at the end of the process, there won't be a t in the answer. It's basically, you can think of it, it's integrated out. So the whole integral depends only on s, which is why we call it a function of s. Now, what we did was we went through and did a lot of cases. So we said, well, what if our function is a power, t to the n? Well, that came back to the gamma function. Well, what if it's sine or cosine? Okay, we can do that. What about the exponential function? Oh, we can do that. And so if you take what we did last time and say, look at all the possibilities, then what you have is on the left-hand side, this is the function f of t. The right-hand side would be the output. All right. And why are we doing that? Well, if you think back to derivatives, you might remember that there's this rule for derivatives where it says, well, you take a limit as h goes to 0, and then something, something, something. And then we're like, oh, not limits, please. No. But we don't do limits to take derivatives anymore. What we do is we say, hey, there's a whole bunch of rules. And if we know the rules, we can use that. And that's what we're doing right now, is we're developing our set of rules. And so that's where we're at. We're saying, okay, here's a lot of functions that we have. And then we'll talk about ways that things combine together. And we're only going to do very simple things when it talks about how things combine together. So that's what we're doing. As already mentioned, we don't expect you to memorize this because we're going to throw a lot at you. But you should know how to use it. And we're going to do some practice with using this today. But before we get to our practice using it, let's make another rule. All right. So, our first thing. We're going to talk about a function. It's called the unit step function. And the graph is really nice. So, if you were to graph this, it has the following. It's 0 if you're below 0. So it comes in at 0. And then it jumps up to 1. So unit is the idea that a 1's involved, so it's a 1. And step is you step up. Okay, so that's why it's called the unit step function. But when I first learned about this function, the name I heard was the Heaviside function. And I thought, what a fantastic name! Because there's like two sides to this function, and this side is heavy. And so it's the Heaviside. Wow, brilliant. And then it turns out, no, that's not why they call it the Heaviside function. There's actually a mathematician whose last name was Heaviside. And I thought, well, okay, what a shame. It was a great name. Now it's not that exciting, but all right. So that's our basic function. And then we're going to see this several times. And there's a particular one. It's going to be so common, we're going to actually be marking it as u sub a. So there's a subscript. And what the subscript tells you is how far you shift over. So the original function, it jumps up at 0. U sub a jumps up at a. So you come over, and then you jump up. So this is u sub a. All right. So now our question. What's the Laplace transform? Well, when we don't know, we go back to our definition. So that's why it's nice to know our definition. So the Laplace transform of u sub a, by definition, integral 0 to infinity of e to the minus s times t, u sub a of t. And by the way, we're going to assume here a is positive. I don't know if we've really emphasized this last time, but maybe we should just pause for a second to make an observation, a comment, if you will. Look at our definition of Laplace transform. Where do we care about the function f of t?
Between 0 and infinity.
Yeah, between 0 and infinity, because that's the only place where this integral happens. So what happens before 0, we don't care about it. You might say, boy, that's pretty harsh, really going against those negative values. But the idea here is sort of to say, look, we really care everything starting at 0 and saying what's going forward, moving forward. And so implicit to almost all our discussions is there's sort of this inherent, we really care about what's happening for the positive parts. Okay, so here we can assume a is positive. So how do we carry out such an integral? Now, in case you're wondering, what does this look like? Well, we know what an exponential function looks like. That's not too surprising. Exponential decay. What does the use of a of t do to that function? So yeah, whenever you have this makes things piecewise. This is a great way to describe it. And essentially, you should think of it as like use of a is like an on-off switch. If I'm before a, I'm off. If I'm after a, I'm on. 0 and 1. So before a, nothing. After a, the exponential function. So that's what this does. So in terms of the integration, how can we do it? Well, someone said piecewise. But really, what piece do we care about? Yeah, a to infinity. The part up to a is going to be 0 automatically because of the use of a. So we can say this is the integral a up to infinity e to the minus st dt. And now we're like, wow, this is wonderful. We like this integral because we can do it. What does that integral turn out to be? Okay, there's a negative 1 over s, e negative st. Now, in case you're following along, where is that coming from? We're integrating with respect to t, and the integral of the exponential function is the exponential function. And then we have to say, well, wait, it's not just t upstairs, there's this minus s. And from our perspective for right now, minus s is treated as a constant when we're doing the integral. So you have to divide by that constant. So that's where the 1 over s is coming from. And then the minus because there's a minus. But don't forget, we have to evaluate. At infinity, what happens? You get 0, because the exponential function drives it to 0. So this is 0, subtract, minus 1 over s. Now we plug in t equals a, e to the minus s times a. Or we could write this as e to the minus a times s divided by s. And there we go. Now, if you think back, and this is probably great for people who have good memories, what does this vaguely remind us of, this unit step function, in terms of our table? So suppose I throw our table up here. What does it kind of look like? Looks a lot like what happened to 1. See, 1 would end up with the 1 over s. So what we can think of it is like this part up here, that's really what's happening because of that unit step function. And so our intuition will tell us, and we're going to go into more detail about this, not today, but in another session, that when we see things that look like this, we're going to say, oh, there was a unit step function involved. Something happened that went on and off. In particular, on and off at a. So that's what we're going to see. Okay. Now, why do we care about the unit step function? Well, the answer is because we can use it to rewrite our piecewise functions. So we're going to do an example here. Now, there's no Laplace transforms in this example here. This is just mostly saying, hey, we like unit step functions. This is what we want to get to. And what do we do? Well, we have this sort of off-on type behavior. And so what we want to do is to say, can we rewrite this f of t sort of as a one-line form? So instead of having this case analysis, case by case, say, well, no, it's just f of t in this nice one simple expression. Simple, of course, we can put in quotes. And so before we tackle that, let's do a simple example. Suppose I want the following. And namely, I'm going to come along. Then at A, I'm going to jump up to 1. Keep going until I hit B, where I go back down to 0. So think of it as I'm just going to be on for just a little bit of time. Turn on at A, turn off at B. But besides that, I'm 0. Can we find a way to write this simply in terms of the unit step functions? Okay, so we've had a suggestion. So let's write this down and let's check it. U sub A minus U sub B. So remember the A and the B says when do we turn on and off. So before A, so I'm over here, what are the values for U sub A and U sub B? They're both 0. 0 minus 0 is 0, which is good. Between A and B, what happens? 1 minus 0. I'm on and I'm off. 1 minus 0, which is good. That's what we want. After B, what happens? 1 minus 1. So I'm back to 0 again. So this works. So this is a great way to say, hey, if I want to turn something on and turn something off, life is good. Well, what we can think of as a piecewise function, we can say, well, okay, we'll just turn on and off our pieces. So we have really two things that need to happen. The 0, it's just everything's going to be automatically 0 unless I'm turning something on or off. Okay, so we say, okay, for the first one, that's 3. That's the function. I want to turn 3 on, and I want it to be on between 1 and 2. So U sub 1 minus U sub 2. And that would be the function which is just 3 between 1 and 2. So I turn on the 3, I turn it off. Now what do I do? Well, now I have to turn on the other part. So I can add 7 minus t squared, that's my other piece, and turn it on at 2, turn it off at 3. And there we go. Now, there's things we can do to this if we wanted to. We could, for example, rewrite this as 3 times U sub 1. Then say, well, hey, look at the U sub 2's. There's 2 of them. So we could put them together. There's minus 3 here. There's 7 minus t squared there. So we could write it as 4 minus t squared U sub 2. And then there's a single U sub 3 at the end. So minus 7 minus t squared U sub 3. So that's another way we could write it. But the moral here is we can turn on and off our pieces as we need to. And now we say, okay, once we understand how to do a Laplace transform, when we have a unit step function times a function, which we'll get to eventually, we'll be able to do the Laplace transform of things like this. So this is a way to handle things happening piecewise. That's the moral of the story. All right, good. That doesn't seem so bad. Any questions about this part? All right. Well, now we'll get to the next part, which is our practice. We have some rules and we have some practice. So now practice. So we want to practice finding the Laplace transform of some functions. And we know a couple things. We know the Laplace transform is nice when it comes to addition and multiplication by numbers. In other words, when we see things like addition and subtraction, or we see constants, we say those don't bother us, we can handle it. Addition says break it up into small pieces. pull constants in and out as needed. No worries. But what we want to do is we want to say, hey, we invested time in our rules. Let's not have to go back and reinvent things. Let's see if we can't rewrite things so that it falls into our rules. So let's look at our pieces. Can we handle e to the 2t? Yes, that's one of our rules. Can we handle t cubed? Good. 1? Yes. Cosine squared? Can we handle cosine squared? I don't think cosine squared's on our list. Cosine's on our list. You might say, well, wait, just do cosine times cosine. We haven't learned how to do multiplication yet. Oh, that's not as exciting as you think. And you're probably thinking, I didn't think it was exciting to begin with, Steve. You're right. So cosine squared is not on our list. But what is on our list? Cosine. You're probably thinking, okay, we can just write the square and get partial credit, right? No, 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 that's not what I'm thinking. What can you do to cosine squared? Okay, so there's lots of great mumbling going on that involves trig identities. I think collectively you all said the right pieces. Probably individually you said it too, it's just hard to make out. So cosine squared of an angle, this is a power reduction. It's almost like we expect you to remember stuff. This is Calc 2. Use this a lot. 1 plus cosine twice the angle over 2. So that's the power reduction formula for cosine. And what that allows us to do is rewrite cosine squared in terms of cosine. In other words, it says, hey, let's rewrite this in terms of something we know. Because if it's something we know, well, then we know it. And we like to know stuff. So let's first off rewrite this. So this is the Laplace transform. We have 5e to the 2t plus t cubed minus 7. And what will this become? Three plus 3 cosine 10t. Yeah, remember to double the inside. So double 5t is 10t. All right. Now, because we're just starting out our practice, we're going to go a little bit slow in the sense we're going to be really clear about what we're doing next. And that is, we're going to break this into pieces. Oftentimes at this step, we almost write down our answer. But let's be careful. So, well, 5 comes out. Laplace transform e to the 2t. Then the t cubed, so Laplace transform of t cubed. We have minus 7 plus 3. We can put those together as minus 4. So minus 4, Laplace transform of 1. And then plus 3, Laplace transform of cosine 10t. And then at this point, we start looking at our table. Okay, so e to the 2t, does that show up on our table? Okay, what does it become? Yeah, so e to the 2t become 1 over s minus 2. Okay, so we have 5 times 1 over s minus 2. Okay, how about t cubed? Is that somewhere on our table? Okay, there's t to the n. What will it become? 3 factorial over s to the 4th. 3 factorial also known as 6. Okay, so plus 6 over s to the 4th minus 4. Okay, 1 is 1 over s. So 4 times 1 over s plus 3. Okay, cosine of 10t. Can we do that? Yes, because we do have cosine, something t. What will it become? So s upstairs, s squared plus 100. So s over s squared plus 100. Okay, and now what do we do next? Yeah. we circle it. That's what we do. As Steve says, as he draws a rectangle. We're not told to simplify, and so there's a wonderful rule of thumb. If you're not told to do something, don't do it. It's wonderful advice, because oftentimes it'll take you lots of energy, and in some sense, when it comes to Laplace transforms, we don't want to put things together. We actually want to do the opposite. We want to get good at pulling things apart. That's where we're going, is to really stretch and pull things apart. But that's a story for Friday. Okay, that one's done. How about here? Next one. T to the 3 halves, can we do that? Cool. 10 sine 4t cosine 4t? Not yet. What do we do? Trig identity. Good. Which trig identity? Sine 2 theta equals 2 sine theta cosine theta. Yes. Nice. So, I can hear someone going, yes, like trig identities, yeah! Exactly, that's the spirit. That's the spirit. Okay, so this would be the Laplace transform of t to the 3 halves. And if we apply the identity, what will this become? Five sine of 8t. All right. So again, we can break this up into two pieces. T to the 3 halves plus 5, and doing the Laplace transform of sine of 8t. So this step right here is where we're using the fact that we have something which is nice and linear. Okay, what happens to t to the 3 halves? So if we pull up our list, what does that become? So t to the 3 halves, it's not a whole number. So n factorial is when it's a whole number. So it's t to the a, so a is 3 halves. So it'll become what? Okay, gamma. Some of you are probably thinking upside down L, maybe? So yeah, this is the gamma. So it'd be gamma of 5 halves over t to the 5 halves plus 5. Okay, Laplace transform sine of 8t. So sine of 8t will become what? 8 over s squared plus 64. See, we're using our table. We're not like, oh, let's go back to the definition. No. Table. Table's your friend, which is why it's good to have one handy. S squared plus 64. Now this is okay, but let's suppose we wanted to say, what is gamma of 5 halves?
On the bottom of the gamma, is it supposed to be T or S?
It's supposed to be an S. You're right. See, that's a very badly written S, see? Now that I write it more clearly, you can see, oh yes, that was an S you had written down. Thank you for helping me. What is gamma of 5 halves? Well, the answer is we don't really know that one. But there's a nice fact about gamma. This is the same as 3 halves, gamma of 3 halves. This is the property about the gamma function, where gamma of x plus 1 equals x gamma x. And you're like, okay, Steve, great. You went from 5 halves, which you don't know, to 3 halves. And 3 halves, we don't know that one, but we do it again. What is gamma of 3 halves equal to if we apply the rule again? Yeah, 1/2 gamma of 1/2. Oh, somebody knows gamma of 1/2. So in case people are wondering, wait, what's this magic thing Steve is doing here? This is x plus 1 equals x gamma x. This is how the gamma function behaves like factorial. And then gamma of 1/2, we didn't actually prove it, but we stated it. Do you remember it? It's square root of pi. So we could say our answer becomes 3 square root of pi force all over s to the 5 halves. And then 5 times 8, we could write that as 40 over s squared plus 64. And there's our answer. All right. Well, 2 down, 1 to go. We should finish it, right? Complete the trilogy. Now here, we've got 2 functions, sinh of 2t. Can we do that? Is that on our list? Yes, that'll be pretty straightforward. T squared e to the minus 3t, can we do that? Yeah, so we t to a power, exponential function, that's on our list. Okay, so again, we can break it up into 2 parts. Sinh 2t and t squared e to the minus 3t. Okay, so sinh, we can put it here. Sinh of 2t will become what? Two over s squared minus 4. Okay. Plus, now t squared e to the minus 3t, I'm going to move this over here. What will that be? So there's the rule. Yeah, so 2 factorial is 2 over so it's s minus minus 3, which is s plus 3, good. To what power? To the 3. Because n equals 2, so 2 plus 1, 3. All right, and then we're happy with that. All right. So you notice, we didn't actually ever have to go back to the integral. The whole point here is not to have to do the integrals anymore. It's to have that table to refer to and use the table to say what happens to the pieces. And now we have our individual parts. Okay, well that's great. That says if you have a function, what's the Laplace transform? But we also have to go the other way. So that's the inverse Laplace transform. And I think somebody asked the question, why? And the answer is, you'll see. Just wait, it's coming. It's going to be glorious. Okay. Now, you might notice here that there's these minus 1s. That's how you know you're dealing with the inverse Laplace transform. Think of it as the going backwards part. And when you are doing the inverse Laplace transform, we don't even have the integral to look at. So we can't do anything other than look for something in the table it matches. Now keep in mind, we're allowed to do things. We're allowed to rewrite. And that's the big theme, is how can you rewrite these so that you have something that matches what's in the table. Now there's some easy things you can do, like breaking up addition, because the inverse Laplace transform is still going to be linear. Then there's going to be the more interesting things, which we're going to talk about on Friday, things like partial fractions. All right. So the key is, look for things that we've seen before, and keep in mind, constants are easy to move around and easy to change names. So we start with the first one. 3 over s plus 4. Does that look like anything on our table? Which one? Yeah, e to the ct. Now you might say the 3, but we don't care about the 3. Constants can be pulled out. So this is the same as pulling the 3 out. Inverse Laplace transform of 1 over, and then I'm going to really emphasize s minus minus 4. What I'm trying to do is I'm trying to make this expression fit my mold. My mold is 1 over s minus c. Okay, so 3 is 3. If I have 1 over s minus c, where did I come from? Yeah, so e to the negative 4t. And that's the answer. Okay. Next up. Inverse Laplace transform 5 over s minus 1 to the 6. Does that fit anything here? Okay. There was a yeah. Which one? it looks like this, right? So it's s minus something to a power. The n factorial is a number. Numbers can be moved in and out. So don't worry about anything that's a number. Always remember you can move it in or out. It's the parts that involve s that have to match. Okay, so keeping in mind that we want it to look like this, well, we have the s minus something. The 6, well, we could write that as s minus 1 to the 5 plus 1, just to emphasize where we're going. What do we want upstairs if we're going to match here? 5 factorial. Now you see, we need to somehow cancel, because we only had 5, so we just have to cancel that exclamation mark, right? People are like, yeah, that sounds right, Steve. Other people are like, I don't think that's right, Steve.
Oh, yeah, do it,
Do it, Steve, do it, yeah. Okay, I'm getting egged on here, but what should be here? Yeah, actually, it's pretty close. It's 4 factorial. So if you have 4 factorial out front, that will cancel with 5 factorial, almost all of it, except for just the 5. And now we're great. That 4 factorial in the front, what's another way to write 4 factorial? 1 over 24. And what does this become? Yeah, so C is 1, N is 5. So C is 1, N is 5, we see e to the t and t to the 5th. And there's our answer. Okay. Great. Now the fun one. 9s minus 7, s minus 1 squared plus 16. What does it look like? It looks like the cosine or the sine, right? There's some things that are like, I'm a little skeptical here. Now, is it exactly the cosine? No, it's not quite. What's the problem? Well, first off, we'd have to have s minus c upstairs. There's a 9 here. So let's do something. We can write this in the following way. So Laplace inverse. I can think of it as 9 times s minus 1. And I'm going to leave a gap here and talk about it. And that would be great. If we just had that, we'd feel pretty good about it. If we just had this, what would we have? It'd be the cosine. Pull out the 9. But that's not what we have. There's this gap here. What goes here? Plus 2. Because then you have minus 9 plus 2 is minus 7. And now we're like, it's not quite cosine. Now, if we didn't have the s minus 1, if we just had the 2, what would we see? Looks a lot like the sine. So what can we do? Yeah, we can separate, pull it apart. See this word up here? Rewrite. That's a lot of the key, is learning to rewrite the expression to something which is easier for us to work with. So in our case, we say, okay, great. So we're going to pull out, in the first term, we're going to have 9, the inverse Laplace transform, the first piece. And I should point out that it's really easy to separate when the addition is in the upstairs. We like addition upstairs. When addition isn't downstairs, not so fun. Not so fun. Okay. Now the next piece, let's anticipate. It's a kind of a dangerous thing to do, is to anticipate. What do we want? We want it to make it look like the part from the sine piece. What would we like to have in the upstairs? We'd like to have the 4, because that matches this. What do we currently have? So how do we make it be a 4? Yeah, so we can make it 4. And now, put out a half in the front. Now, if you didn't see that right away, that's okay. Just put a 2 here, and then just stare and say, oh, I need to make it a 4, so put another 2 and then put a half in the front. Okay. And now we're almost there. So our first piece will be what? E to the t cosine of 4t plus a half, and the second piece will be e to the t sine of 4t. And there we go. So that shows you an example of something which is getting more close to what we will anticipate that you'll be able to do, namely pull into the individual pieces that we need to rewrite. Okay, so that's good. So now we said, aha, we can go from a function of t to a function of s using our table. We've seen using our table how to go from functions of s's back to function of t's. In other words, we can do Laplace, we can do inverse Laplace. But still the mystery. Why are we doing this? Where does this come into differential equations? That's the next rule. This is the good stuff. All right. So here's the idea. And the punchline is, suppose I want to take the Laplace transform of a derivative. Well, the Laplace transform of a derivative, there's an integration involved. And so we're going to do the following. We're just going to follow the computation. It says, well, I'm going to do integration by parts. So using the definition of the Laplace transform, and I say, I'd like to change that f prime. I'd like to change it to f. So we're going to make this part, f prime t dt, that's the dv term, the part that we integrate. The rest of it, e to the minus st, that'll be our u term, the part we differentiate. So it's easy to integrate a derivative. So that says v is f of t. So the integral of u dv is u times v minus the integral of v du. And so the derivative here, the minus s comes down. So we've done integration by parts once. Now we do our evaluation, as almost always happens. Well, always happens really for us. At infinity, the exponential term dominates, things go to 0. So we subtract what happens at 0, in which case exponential term goes to 1, and we have the function at 0. So the minus f of 0 comes from the evaluation. And then in the second part, we pull out the minus s. So we have an s in front. And then our great, whoa, we recognize this. Namely, the integral that's left is the Laplace transform of our function. And so we can take the Laplace transform of the derivative and we can relate it to the Laplace transform of the function. In essence, it's not hard to do a Laplace transform of derivatives. It's pretty straightforward. Now that's just one derivative. But we can do any number of derivatives that we want, because say I want second derivative. The second derivative is the derivative of the derivative. So what happens here is if I want to do the Laplace transform of the second derivative, I can apply the rule. And so let me just sort of copy this down. The Laplace transform of a derivative, it's s times the Laplace transform of the function minus the function of 0. So now apply the rule above, but to where the function is the first derivative. S times the Laplace transform of the first derivative minus f prime of 0. And then copy the rule again. Hey, Laplace transform of the first derivative, I know that, I'm copying the rule above. So you get s squared, Laplace transform of the function, minus s times the function at 0 minus f prime of 0. And you can repeat, 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 repeat. And if you do that, you have this nice general formula. And it's written down here. It says, I can take the Laplace transform of any derivative. And it's related to the Laplace transform of the function itself by multiplying by s to the power n. So somehow, multiplying by s is like taking an antiderivative. It's like, wow, that's really cool. It makes it super easy to take the antiderivative. It's like, you get an s, you get an s. All these terms get an s. But then there's some initial conditions. And the way you can think about it, say, okay, this first term is s to the n. You'll notice the next term is s to the n minus 1, s to the n minus 2, and so forth all the way down. And then you have the function at 0, first derivative at 0, and so on again all the way. In practice, you will never ever need these two pieces. What happens to the first derivative, what happens to the second derivative. But in principle, we can do it for any ordered derivative that we want. Okay. So, let's do an example. There's some boxes here. This is our choose your own adventure. Where do you want to go into that box? 7. And then someone said 4. Okay, so there are two boxes. There's a 7 and a 4. So, we have x double prime plus 7x prime minus 4x is equal to e to the 2t sine of 5t. We're also told x of 0 is x prime of 0 equals 0. So these are some initial conditions. And we always will have initial conditions in these problems. So Laplace transform is built for initial value problems. If you don't have initial values, you don't use Laplace transforms. It doesn't make sense. And the goal is to say, hey, we want to say what's the Laplace transform of x? All right. Well, that sounds like a good challenge. How do we go about it? So, as a reminder, we currently know x double prime plus 7x prime minus 4x is equal to, suspicious gap, e to the 2t sine of 5t. What can we do?
Yeah, apply the Laplace operator.
Okay, so the key idea here is if two things are equal, then if we plug it into this Laplace transform, our Laplace operator, the results are still equal. Okay, well, we can break up over addition and subtraction. So this is the same as the Laplace of x double prime plus 7, the Laplace of x prime, minus 4, Laplace of x. And then there's the other side. We'll come back and visit the other side in a few minutes. We're going to spend some energy on the left-hand side. What can we do to the Laplace of x double prime? We can rewrite it. Good. Is there a rule that helps us rewrite? Steve says, as he copies down the rule. Is there a rule that helps us rewrite the second derivative? Yeah, there is. Yeah. So the second derivative, if I want to take the Laplace transform of that, is the s squared. Because, second derivative, two derivatives, so I need to multiply by two s's. So this part will be s squared. But then we have to, multiply by the Laplace transform of x. We're calling that capital X. So capital X of s. So that's the Laplace transform of x. But don't forget, we have to subtract s, our function at 0, that's x of 0, and subtract the derivative of the function at 0. Okay, so that's the first piece. What about the second piece? Can we do something with this? Yeah, we can apply this rule. So this is s capital X of s minus what's happening to the function at 0. What about this last piece? What would that be? That's our piece that we're looking for. So that's the left-hand side. Now we can simplify. Do we know anything about these pieces where I have x of 0 or x prime of 0? They're 0. So they all go away. So now we have the following. We have s squared times x of s, 7s times x of s, and minus 4 times x of s. So that would be s squared plus 7s minus 4 times x of s. And remember, that's what we're trying to solve for. Equals something. Well, what haven't we done yet? Yeah, this stuff on the right. So we go back to our table. Is this on our table? Yeah, it's here. E to the 2t sine of 5t is equal to what? 5 over s minus 2 squared plus 25. Now, our goal is to find x of s. We're almost there. What's the last thing we need to do? Divide this part over. So we get x of s is equal to, well, 5 s squared plus 7s minus 4 times the s minus 2 squared plus 25. So there is the answer to the question, because our question was find x of s. And now at this point you're like, okay, this is good. If we wanted to find x of t, what would we do now? What would be our next step?
Find what that is.
Yeah, find what this is. If we could find the inverse Laplace of this, that would tell us what x of t is. That would give us our answer. And so we have a game plan. Here's the game plan. We're not going to actually have time to do it today, but we're going to do it next time. So, if we have an initial value problem, we do the following. We take the Laplace transform of both sides. That's what we did. We took the Laplace transform of both sides. We use the tables, and we use our rules for derivatives. And the rules for derivatives will show up on our table eventually. Then we do step 2. We solve for x of s. We say, great. So we've done the first half. Next time, we go into the second half. It says, simplify. Simplify this expression so that it looks like the individual pieces are things we can do the inverse Laplace transform. And then we actually do the inverse Laplace transform, and we have x of t. So that's how we use the Laplace transform to solve differential equations. All right, thank you. That's it for today. And we'll pick up again next time.